Hi, good day. So for today, we are going to talk about the repeated measures ANOVA or repeated measures F-test. Repeated measures ANOVA is one of the ways on how we can find the significant difference between three or more sets of data that came from dependent samples. Repeated measures ANOVA can only be used if the data that we have are normally distributed, and therefore, repeated measures ANOVA is a type of parametric test. Also, because in repeated measures ANOVA, our data are normally distributed, then the most appropriate level of measurement that we should use here should be under interval or ratio scale. To give you an example on how repeated measures ANOVA works, let's have here an example research entitled The Growth of Tomato Plant Using Fertilizer X. Now in this research, let's assume that fertilizer X claims that it can cause significant growth in tomato after 2 weeks of application. Now in this research, we set up 5 different samples of tomato plants and we obtained their heights before the application of fertilizer X, 1 week after the application of fertilizer X, and 2 weeks after the application of fertilizer X. Now take note that the data in before column, week 1 column, and week 2 column only came from the same set of samples. These samples which are repeatedly measured every week. Hence the name repeated measures ANOVA. And these samples are dependent samples. Now we also obtained the total for each column, like for column number 1 or for the before column, we have here 5 plus 6 plus 5 plus 8 plus 4, and that's 28. For week 1, that's 30.2, and for week 2, that's 35. And we also obtained the mean for each column. Okay, so that's 28 divided by the number of data in first column is 1, 2, 3, 4, 5. So 28 divided by 5 is 5.6. For column number 2, the mean for column number 2 is 6.04. And the mean for column number 3 is 7. Now aside from this, we also obtained the mean for each row. Okay, like for sample A, we have here 5 plus 5.5 plus 6. And the mean for this row is 5.5. For sample B, that's 6.4. For sample C, that's 5.17. For sample D, that's 9.33. And for sample E, that's 4.67. Okay, and we also obtained here the grand mean. The grand mean is just the average of these three means in columns. Okay, so we have here 5.6 plus 6.04 plus 7 divided by 3, and that's 6.21. That is actually our grand mean. Okay, now obviously there are variations in the results here. Okay, and again, these variations may be caused by our independent variable or may be caused by random error or random differences. So again, just a little review. Variations may be caused or may happen due to, number 1, independent variable. We call it the between the group variation. Okay, in ANOVA, that is actually represented or numerically represented by our SSB or sum of squares between the group. Okay, or variations may happen due to random error or differences, okay, which we actually call the within the group variation. Now in ANOVA, the variations due to random error or differences are actually represented by our SSW or sum of squares within the group. However, our sum of squares within the group or within the group variation can still be classified or can still be divided into two. Okay, our variations can actually be caused by just random error, and therefore in ANOVA we will have here the SSE or the sum of squares for error, or the variations may actually be caused by the differences of our subjects or the individual differences of our subjects. Okay, and that is actually represented in ANOVA. That is actually represented by our SSS or the sum of squares subjects. Okay, and therefore our sum of squares within the group is just the sum of sum squares error, okay, this one, and the sum squares subjects. Now in repeated measures ANOVA, there are actually two values that are important for us to be able to find our F value or ANOVA value. The SSB or the sum of squares between the group, and the SSE or the sum of squares for error. However, for you to be able to compute the SSE, we need to find first the SSW, or the sum of squares within the group, and the SSS, or the sum of squares for subjects. Now, how do we compute these four values, the SSB, SSW, SSE, and SSS? Okay, so let's have here this computation. Let's have first the SSB, or the sum of squares between the group. For SSB, or sum of squares between the group, we have here n. N is actually the sample size. In this case, we have here 1, 2, 3, 4, 5. 5 samples. Multiplied to the summation of the squared difference of the mean for each column. Okay, mean for each column. And the grand mean, GM. Okay, and by plugging in all the data that we had earlier, then we will have here SSB, or sum of squares between the group, is equal to, again, our sample size is 5, multiplied to, for our first column, we have here the mean of 5.6, minus, again, our grand mean is 6.21 squared, plus for the second column, we have here 6.04, minus, again, our grand mean is 6.21 squared, plus for the third column, we have here the mean of 7, so that's 7, minus 6.21, our grand mean, okay, squared, okay, and by plugging in all these data in your calculator, then we will have here SSB, or sum of squares between the group, is equal to 5.1255. Now, for the SSW, or the sum of squares within the group, our formula is SSW is equal to the summation of the squared differences of the individual data in column number 1, okay, and the mean for column number 1, plus the summation of the squared differences of the individual data in column number 2, and the mean for column number 2, plus the summation of the squared differences of the individual data in column number 3, okay, that's C3, and the mean for column number 3. Okay, and by plugging in all the data that we had earlier, then we will have here SSW is equal to, for the first column, we have here 5, okay, that's actually our first data in first column, 5, minus the mean for the first column, that's 5.6 squared, plus, okay, our second data in first column is 6, so that's plus 6, minus, okay, again, the mean for first column is 5.6, okay, squared, and we are going to do that in all the data that we have in the first column, okay, plus, okay, for the second column, we have here 5.5, okay, minus the mean for the second column is 6.04 squared, okay, plus our second data in the second column is 6.2, minus, again, the mean for the second column is 6.04 squared, and again, we are going to do that in all the data that we have in our second column, plus, okay, for the third column, we have here, for the first data, we have here 6, minus, again, the mean for the third column is 7, okay, squared, plus 7, minus the mean for the third column is 7 again, okay, squared, and we are going to do that again in all the data that we have in our third column, and by plugging in all this data in your calculator, then we will have here the value for SSW, or the sum of squares within, which is equivalent to 43.232. Now, for the sum of squares for subjects, or SSS, our formula is SSS is equal to K. K is the number of groups of data in our research. In this case, we have here 1, 2, 3. 3 groups of data. So, our K here is 3. Multiplied to the summation of the squared differences of the individual mean for each row. Okay, so those are 5.5, 6.4, and so on and so forth. Okay, and our grand mean. Our grand mean is 6.21. And by plugging in all the data that we had earlier, so we have here SSS is equal to, again, our K here is 3. Okay, 3. Multiplied to, for our first mean for row, okay, for the first row, we have here 5.5, minus, again, our grand mean is 6.21 squared, plus 6.4. Okay, that is actually our second mean for this row, minus the grand mean, which is 6.21 squared. And again, we are going to do that in all the data that we have here. Okay, and by doing this in your calculator, then we will have here SSS is equal to, or the sum of squares for subjects is equal to 41.1834. Now, how do we get the SSE, or the sum of squares for error? Because this one is very important for us to be able to compute our F or ANOVA value. SSE is just the difference of our SSW and SSS. So that's 43.232 minus 41.1834, and that's 2.0486. That is now our SSE, or the sum of squares for error. Now, the next things that we are going to do are to determine our null hypothesis, the degrees of freedom between the group, the degrees of freedom within the group, the degrees of freedom for subjects, the degrees of freedom for error, our alpha level or level of significance, the critical value, and our decision rule. For the null hypothesis, our null hypothesis is there is no significant difference on the plant growth before, 1 week after, and 2 weeks after the application of fertilizer X, or the data before the application of fertilizer X is just equal to the data 1 week after the application of fertilizer X and 2 weeks after the application of fertilizer X. For the degrees of freedom between the group, again our formula is K minus 1, where K is actually the number of groups of data. Okay, so in this case again we have 1, 2, 3 groups of data, and that's actually 3 minus 1. 3 minus 1 is equivalent to 2. Therefore, our degrees of freedom between the group is 2. Now, in our F distribution table later, that is actually represented by V sub 1. Our degrees of freedom between the group is represented by V sub 1. For the degrees of freedom within, our degrees of freedom within is equal to N. N is actually the number of the data that you have minus K. K is actually the number of groups of data. In this case, we have actually 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 data. Okay, so that's 15 minus again, our groups of data here are 1, 2, 3. 3 groups. Okay, so that's 15 minus 3, and our degrees of freedom within is equal to 12. For the degrees of freedom for subjects, we have here N minus 1, where N is the sample size. So we have here 1, 2, 3, 4, 5 samples, and that's actually 5 minus 1. 5 minus 1 is 4, and therefore our degrees of freedom for subjects is 4. For the degrees of freedom for error, that's degrees of freedom within minus degrees of freedom for subjects. So that's 12 minus 4, and our degrees of freedom for error is 8. Now, this degrees of freedom for error is actually symbolized as V sub 2, okay, V sub 2 in our F distribution table that we are going to use later. Now, for our alpha level or level of significance, our level of significance is 0.05 or 5%. This 5% is represented by this region in our F distribution. This region is actually known as the rejection region. If our F value or if our ANOVA value falls under this region, then we need to reject our null hypothesis. Now, if our value falls under this region, then we need to accept our null hypothesis. Now, clearly, there is a distinct line that separates the acceptance region and rejection region. The question is, what is the value of this distinct line here? The value of this distinct line here is actually determined by our critical value. And to know our critical value, there are actually 3 things that we need to determine first. Our degrees of freedom between, our degrees of freedom for error, and our alpha level. Now, let's take a look at our F table or ANOVA table in order for us to determine our critical value. This is the critical value table for ANOVA or F test. Here, we know that our alpha level or level of significance is 0.05 or 5%. Our degrees of freedom between the group or V sub 1 is 2. And our degrees of freedom for error or V sub 2 is 8. By intersecting the value under 2 as the degrees of freedom between the group or V sub 1 and 8 as the degrees of freedom for error or V sub 2, then we can say that our critical value for F or F crit is 4.46. Now, after looking at the F distribution table, we now know that our critical value for F is 4.46. And therefore, this line here is equivalent to 4.46. Now, our decision rule here is that if our computed f value is greater than or equal to our critical value for f, which is 4.46, then we need to reject our null hypothesis. Now, how do we compute this fcom or this f value here? Now, this is the ANOVA table, and it has actually 5 columns. The first column is the sources of variation. The second column is the sum of squares. The third column is the degrees of freedom. The fourth column is the mean of squares. And the fifth column is the f value or the ANOVA value. Now, the source of variation is primarily divided into two. We have here the between the group variation and the within the group variation. However, as mentioned earlier, the within the group variation is still divided into two. The variation that is caused by random error and the variation that is caused by the differences in our subjects. That's why we have here subjects and error as subsets of within. Okay? Now, for the sum of squares between the group, that was already determined earlier. And that was actually 5.1255. Okay. For the sum of squares within the group, that's 43.232. For the sum of squares for subject, that's 41.1834. For the sum of squares for error, that's 2.0486. Okay. And we have here the total. Okay. Now, the total is just between plus within. Okay, because subject and error are just, again, subsets of within. Now, for the degrees of freedom, the degrees of freedom for between is 2. The degrees of freedom for within is 12. The degrees of freedom for subjects is 4. And the degrees of freedom for error is 8. And we have here a total of 14. Now, again, here 14 is just the sum of 2 and 12 here, the between and within, because subjects and error here are just subsets of within. Okay. Now, for the mean of squares, for us to be able to get the mean of squares, we just need to divide our sum of squares to our df. And so, the mean of squares for between the group, that's actually 5.1255 divided by 2, and that's 2.5628. Okay. For within the group, that's 43.232 divided by 12, and that's 3.6027. For the subject, that's 41.1834 divided by 4, and that is 10.2959. And for the error, we have here 2.0486 okay, divided by 8, and that is 0.2561. Now, for us to be able to compute our f in repeated measures ANOVA, okay, we are going to divide our ms between the group and our ms for error. Unlike in one-way ANOVA, in one-way ANOVA, by the way, we are actually dividing the ms between the group and the ms within the group. But in repeated measures ANOVA, we are dividing the ms between the group and the mean of squares for error. Okay, so that's 2.5628 divided by 0.2561, and that is equivalent to 9.98. Therefore, our f value or our computed f here is 9.98. Now, let's have here the analysis. For our analysis, we have here, since fcom or the computed f, which is 9.98, is greater than our critical f value, which is 4.46, then we need to reject our null hypothesis, because again, in our decision rule, if our computed f is greater than or equal to our critical value for f, we need to reject our null hypothesis. In this case, 9.98 is greater than 4.46. Therefore, we need to reject our null hypothesis. And therefore, our conclusion here will be there is a significant difference on plant growth before and after the application of fertilizer X. Now, since there is a significant difference in our data, then the next question here is, where can we find that significant difference? Is it between before and week 1? Is it between week 1 and week 2? Or is it between before and week 2? And so to know that, we can actually perform post hoc test after we performed repeated measures ANOVA. One example of post hoc test is t-test. Like we can actually perform t-test between before and week 1, or week 1 and week 2, or before and week 2, just for us to know, or just for us to determine which groups got significant difference. So that is how we can use the repeated measures ANOVA in finding the significant difference between 3 or more groups of dependent data that are normally distributed. Thank you for listening and good day.